Welcome to the University of Kentucky's Center for Applied Artificial Intelligence. Visit us online at caai.ai.uky.edu to learn more.
Hi, I'm Emily Collier with the Center for Applied AI at the University of Kentucky. In this video, we'll introduce some key foundational concepts for understanding artificial intelligence. Yet to understand AI well, we need to begin with critical understanding and a bit of demystifying. AI isn't a monolith, and it isn't magic. It's a collection of methods, models, and applications, and crucially, it's a collection that researchers in any field can engage with. So why does this matter to us, as researchers and educators? Because AI is no longer just in the domain of computer scientists. It's becoming part of this research toolkit being made more and more accessible to everyone. Used well, AI can accelerate discovery, reveal patterns in our data, and free us from repetitive tasks so that we can focus on the deeper critical questions. What excites me the most is this. AI allows us to ask new kinds of questions that were previously too complex, too data-rich, or too time-intensive to even attempt. My goal today is to open the door to AI in a way that's accessible and useful for you. Specifically, we'll do 3 things. Demystify AI, what is it really and what is it not? Explore the major types of AI technologies, from machine learning to robotics, and look at applications in research and higher education, so that you can leave with concrete ideas for your own work. And by the end, I hope that you'll see AI not as something distant or intimidating, but as something that you can begin experimenting with critically, creatively, and productively. When people hear the phrase artificial intelligence, it often conjures very different images. Some think of robots, others think of science fiction, and others think of chatbots like ChatGPT or some other Gen AI outputs. But in research, it helps us to use a much simpler definition. AI is the science of building systems that can perform tasks that normally require human intelligence. So this could mean recognizing patterns in data, understanding language, interpreting images, or even making decisions. And AI is not one single technology, it's more like an umbrella that encompasses a collection of approaches and tools. To put this in context, let me take you on a very short journey through AI's history. The term artificial intelligence was first coined in the 1950s, and back then, researchers imagined machines that could think like humans. Early systems were built around rules and logic, what we would call expert systems. You'd feed in a lot of if-then statements, and the system would make decisions within a very narrow domain. Then, in the 1980s and 90s, came machine learning. Instead of programming the rules directly, we train systems on data and let them learn the patterns. So fast forward here into 2010s, and we see the rise of deep learning. With much larger datasets and much faster computers, we could train models with millions of parameters, unlocking breakthroughs in image recognition, speech, and natural language. And that brings us to today, in an era of large, general-purpose models that can generate text, images, and even multimodal outputs. To make this less abstract, let's break AI down into its 3 essential ingredients. Data, the raw material. Without data, AI has nothing to learn from. So think of research datasets, text corpora, images, audio, sensor readings. This data should ideally be what we call AI-ready, which just means that it's standardized in a way that allows for whichever technology is accessing it to understand it more readily and use it more effectively. Algorithms and models, the recipes or structures that learn from the data. So this could be a simple regression model, or it could be a complex neural network. And then computing power, the engines that make the training and inference possible. Advances in GPUs and cloud computing are what enable today's large language models. And if any of these ingredients are missing, the AI just doesn't happen. And that's the reason we've seen such explosive growth. We've got more data, better algorithms, and faster computers. So we can throw around different definitions, pragmatically or theoretically, of what qualifies as artificial intelligence, but what does hold true is that AI is a broad term. It covers many different concepts, but the overall idea is that the goal of AI is building intelligent systems. Those expert, rule-based systems may not seem intelligent by today's standards, but they set the stage for machine learning. So this image here is courtesy of NASA, and what it shows us is this sort of nesting. So you can call, for example, machine learning a subset of AI, a bit narrower in focus and clearer in definition. Today, the focus is now on a further subset of machine learning, deep learning, which is a specific type of machine learning that uses what are called layered neural networks. And this layering is especially powerful for big tasks like image recognition or natural language processing. So you can think of these concepts as sort of these concentric circles. Understanding these foundations matters because it shapes how we end up using AI responsibly. If AI is just a tool trained on data, then the quality of the results is dependent on the quality of data. If the models are designed for specific tasks, then we need to know their limits. And if computing power drives progress, then access to those resources becomes an issue of equity in research. You're watching this video because you are not a passive consumer of a hype. You seek to understand and be critical, creative users. To help you understand how all of these pieces fit together, I want to take you on a quick journey through the evolution of AI. It really starts with machine learning, which represented this sort of huge shift in how we thought computers could solve problems. So before machine learning, computers relied on rule sets, step-by-step instructions, kind of like a giant flowchart. And that worked well for small, clearly defined tasks, but it couldn't scale. If a problem didn't fit in these predefined rules, the system simply couldn't handle it. Machine learning has changed all that. So instead of following rules, machine learning systems learn from examples. They're trained on large amounts of data, allowing them to recognize patterns and make predictions without needing every instruction written out. And that flexibility opened the door to the rest of modern AI. One of the biggest breakthroughs that followed was the idea of embeddings, a way to translate data, whether it was text, images, or sound, into a sort of shared mathematical language. Embeddings pushed computer vision to new heights, scaled up natural language understanding, and laid the groundwork for what we now call large language models and multimodal AI, the engines behind today's generative systems. From there, we began combining these technologies into AI agents, which exploded in popularity around 2024. Agents can use models like LLMs to reason, make decisions, and take actions, often by calling external tools. And today, we're seeing these same principles extend beyond the digital world into physical AI and robotics, where systems are learning to see, move, and interact with the real world. And all of this, from learning systems to embodied intelligence, began with the shift to machine learning. But if you ask me, the real unsung hero of this story is the embedding, the quiet breakthrough that allowed everything else to connect. So let's begin. Now that we've laid down the foundations, let's open the umbrella and take a look inside. So what are the different types of AI technologies? How do they work? And of course, how do they build and connect? So a reminder of what's in our AI toolkit: machine learning and data science, computer vision, large language models, agentic AI, multimodal AI, and physical AI. Now, you may have noticed a discrepancy where I lumped multimodal in with LLMs on the evolution slide, but this is because they're now a subset of generative AI. So agentic systems arguably also existed before multimodal, and we now have more advanced multimodal agents, so forgive me for the switching, but I promise it's all going to come together. So our baby machine learning is born. AI, at its core, is about finding patterns in data, and there are different ways to go about it. So regression represents predicting a value, such as house prices, while classification predicts a category, such as a positive or negative diagnosis. And both of these require pre-labeled data to learn from so that the model knows how to make those predictions. This is called supervised learning. Clustering, on the other hand, does not require those existing labels, but instead determines its own labels based on similarities and differences in the features of given data. And we call this unsupervised learning. And the advantages of machine learning over other traditional or statistical methods are better accuracy, scalability, and handling of nonlinear complex data, and relying on fewer assumptions about your data and its distribution. And this matters for us as researchers because most of us deal with complex, messy data, sometimes in massive quantities. Machine learning gives us the tools to see the patterns and relationships that we might otherwise miss. For researchers, this approach has transformed how we handle data. So think about projects that involve thousands of survey responses, lab readings, or archived materials. Machine learning lets you surface trends and correlations that you might never spot manually. In education research, for example, machine learning models can analyze student reflections or discussion transcripts to uncover emerging themes, perhaps where students are collectively misunderstanding a key topic. In biology, they can classify cell types or gene expressions at scale. The key idea is that machine learning isn't replacing your expertise. It's amplifying what you can do with your data. Let's take a quick step back and clear up a bit of the mystery around what it means to train a model. So when we say that we're training a model, we're not just dumping a pile of data into a system and say, here, learn something. Training starts with examples. So we give the model a data set that includes inputs with labeled features, information that we already know the answers to. Depending on the type of model, it will start to look for patterns in those features. For instance, a classification model might learn that certain combinations of symptoms tend to align with a particular diagnosis or prognosis. And once the model begins to recognize those patterns, we give it new data. But this time, we hide the correct answers. The model makes its own predictions, and then we compare them to the real outcomes. If the predictions are off, the model doesn't give up. It adjusts its internal parameters, its weights and biases, to reduce error and improve accuracy. That cycle repeats over and over again until the model's predictions consistently line up with reality. So in short, training is about iterative refinement, learning from mistakes, adjusting, and optimizing until the model can generalize to new, unseen data. So when we talk about a model being trained, what we're really talking about is thousands or even millions of these tiny corrections gradually shaping the network into something that can see patterns and make predictions on its own. There are many different types of training algorithms, each with its own way of finding patterns in data. Some are decision tree based, which work a lot like flowcharts, where the model builds for itself. It sorts through the data, branching out at each decision point until it lands on a prediction. Others are vector machine-based, which take a different approach. So they plot data points in a high-dimensional space and draw boundaries, or thresholds, to separate similar groups. And that's the foundation of what's called clustering. And then we have neural networks, probably the most powerful and complex of the group. So you may have heard me mention them several times, and for good reason. At their core, neural networks are systems of connected nodes, a network of tiny mathematical decision points that work together to make sense of data. During training, the model is shown thousands, sometimes millions of examples from a dataset. As each example moves through the network, these nodes perform calculations and adjust what are called parameters, the internal values that determine how the model behaves. Most of these parameters are weights and biases. Weights control how strongly one node influences another. Biases help fine-tune or shift those relationships. And together, they define how information flows through the network and how the model learns. And with each pass through the data, the model compares its predictions to the correct answer. If it's off, it adjusts those parameters just a little bit. And over many, many cycles, the network learns the mathematical patterns that connect the inputs, the data that we feed it, to the outputs, the answers that we want. And that's how it learns to make accurate predictions, even when the right answer isn't known. In the diagram here, you can see data entering in from the left. As it moves through the columns of nodes, each column represents a layer, a stage of refinement. And the more layers a network has, the deeper and more nuanced its understanding can become. The bottom line is that neural networks are all about adjustment and refinement. Predictions don't just travel in a straight line. They weave through this cloud of interconnected nodes, learning, adapting, and gradually finding the best path towards the right answer. With the curtain of machine learning lifted, our next hero enters the stage. So one of the biggest breakthroughs that made modern AI possible are embeddings. At first glance, data is messy. Words are ambiguous, images are complex, and computers, well, they don't understand words or pictures. They only speak in numbers. Embeddings are how we translate meaning into numbers. They take words, sentences, images, even sounds, and represent them as points in a high-dimensional space, a mathematical landscape defined by the model's parameters. And you can think of those parameters as the map makers. They sort of shape how the space is organized. Similar meanings land close together, while different ideas drift further apart. And the result is powerful. A computer can now understand relationships, like how professor is related to university, or how a photo of a cat sits closer to tiger than it does to car. So you can think of an embedding space as kind of like a map, where similar things live closer together and different things live further apart. My example here is flattened into just 2 dimensions, but the idea scales up. So for instance, the concept of a heart might sit close to blood, but it's further away from femur. It's this simple idea that meaning can be encoded into geometry. Now imagine that same map, not in 2 dimensions, but in hundreds. In that vast coordinate space, every word, sentence, image, or sound becomes a vector, a list of numbers marking its location. And what makes this powerful isn't just where the point sits, but how it relates to all the others. So those distances and directions between vectors preserve meaning. And that's how the model knows that cat is closer to dog than it is to apple, or that professor relates more to university than it does to forest. And this translation from raw data into these spatial relationships is what allows AI systems to reason about meaning and not just memorize facts. And when everything, text, images, and sound, can be represented in this sort of same mathematical language, it creates something remarkable: a shared embedding space, a universal stage connecting different kinds of data, text, images, and sound, all speaking that same mathematical language. Now, this idea of mapping meaning into geometry has powerful implications for research. So suppose you work in the humanities. Embeddings can help cluster text by theme, sentiment, or even historical perspective. In the social sciences, they can help visualize relationships between policy documents, interviews, or demographic data. It's a way of quantifying relationships between ideas, giving you a new lens for discovery. So once we could represent meaning in this sort of mathematical-based embedding space, it influenced how we approached computer vision. So computer vision is all about teaching machines to interpret visual data. So as researchers, much of your data is likely stored in images like medical scans, satellite photos, microscope slides. With these types of data, computer vision can do things like detect tumors in X-rays, recognize handwriting, track crop health from aerial images. And they don't just label pictures, they find patterns that we often miss. So how does computer vision actually work? At its core, an image is just numbers, pixels arranged on a grid. The challenge is making sense of those numbers. So another complex concept is the convolutional neural network, or CNN. And here's the idea. The first layers of a model detect very simple patterns: edges, corners, lines. The next layers combine those edges into shapes, circles, curves, and textures. Deeper layers put those shapes together into objects: a cat, a face, or a tumor. It's remarkably similar to how our own visual cortex works, building from the simple up to the complex. Computer vision and CNNs have been around for a while and are still used today. However, more recently, researchers adopted that same architecture that powers language models, the transformer, for vision. So the transformer is what helps us take data into the embedding space. So for computer vision, these are often called vision transformers, or VITs. And the idea here is that images are patched into small tiles, and that these patches are embedded using these VITs and are also given position information so that the model knows the order that each patch had for the larger whole. Each patch embedding will look at all the other patches, learning relationships between them based on their location and other foundational data that already exists in the embedding space. The model then combines these into a single embedding that represents the entire image, and the features of that image have their own vector values. Just like the example earlier, images become positioned by similarity of those features. So cat is close to kitten, close-ish maybe to a 2D drawing of a cat, further away from a dog, which may have similar features but is distinctly different, and then very far away from non-related things like an apple. Modern computer vision models often combine traditional CNNs with VIT, or they might just focus on one method. So in practice, CNNs might be arguably faster or more efficient, but VITs are more flexible and more scalable. I threw in computer vision first since CNNs came before embeddings, but I think we're all familiar with the LLM boom that has happened in the last decade. The embedding breakthrough really pushed this forward. And that same approach that boosted LLMs is what boosted the vision transformer. So this approach is called the transformer architecture. So let's back up and take a look at how that works regarding language. Once we could turn words into embeddings, these numbers living in a space of meaning, researchers built models that could use those embeddings to generate and understand language. The embedding space is filled with data points that came from training on massive amounts of text data. Books, articles, web pages, you name it. And the LLMs learn how words, sentences, and ideas fit together based on their relationships in that space. So this is why they can do things like summarize an article in plain language, draft computer code, or carry on conversations. And when they're extended to create entirely new content, that's what we call generative AI. And Gen AI, at heart, is the prediction of those ideas and patterns. So let's break all this down just a little bit more. Before embeddings, words were treated as isolated symbols. Models didn't understand that words like king and queen are related, or that Lexington and Kentucky have a geographic connection. With vector embeddings, words moved into that semantic space that allowed mathematical relationships to mirror linguistic ones. So like king minus man plus woman approximates to queen. Embeddings became a foundation on which transformers could reason about meaning. So for language, transformer architecture is a process that breaks up text into small chunks called tokens. And these aren't necessarily whole words. They could be just pieces of words or punctuation. But each token is then mapped as an embedding to this high-dimensional vector space. And just like with vision and patches, each language token can sort of pay attention to every other token, no matter where it is in the sentence. So this allows the model to capture context. Who is speaking? What country are we talking about? What depends on what? The transformer layers then refine those relationships, building more connections and richer representations. The output of all of this is a prediction. So based on the user's input, which tokens are most likely to follow? Language becomes a mathematical problem, and the prediction tokens are the solution. So at its core, an LLM is just a very powerful prediction machine. But when you scale it up with billions of parameters and massive data sets, that prediction begins to look a lot like understanding. LLMs are powerful, but they are limited to the data that they've been trained on. So you may notice that if you ask ChatGPT the weather, it's able to give it to you. Does this mean that it's trained on the weather at all times? Of course not. LLMs are able to recognize when an external tool is needed to solve a problem. So in the same way that you might reach for a calculator for a difficult math problem, an LLM knows its limitations. But it also has a defined set of tools that it can rely on to help generate what it cannot. So for our weather example, the LLM is likely calling an API to a weather service where it can sort of scrape the current weather conditions. So tool calling transforms the LLM from a closed system into something much more open through the use of tools. And once a model can use tools, we have the stepping stones for agents. And this is where things really take form. So agents work by combining two processes. Reasoning, using the LLM to sort of think through what step should come next, and acting, actually executing that step, usually through a tool call. And they don't just answer questions, they pursue goals. They plan, take actions, and evaluate results and adapt. So in short, agents shifted AI from being a chatbot into being an autonomous system. So we can imagine this as a structured loop. So I'm searching for the most current research on heart disease. I define this problem to the agent, this sort of goal that I have. The agent will then generate a plan, say review recent articles on PubMed. That plan then triggers action to an API tool that scrubs PubMed. The agent will review the results, and then it will reason again. Did the PubMed search pull the results? And if not, it can reason again, perhaps deciding that there might be something on a preprint site. It can then reformulate the plan and take new action. So this process sort of creates a chain of reasoning and action that is more powerful than a single answer from an LLM. Because agents don't just predict words, they use language as a reasoning engine, coordinating tools and data and memories towards a defined outcome. But to be truly effective, agents need more than just reasoning and tool use. They need memory to track their progress. They employ two types of memories. Short term, what is happening right now in the current loop, and then long term, knowledge that is carried across sections like past tasks, results, or user preferences. And this memory is what allows an agent to stay consistent over time, acting less like a chatbot and more like a research partner. And for researchers, this sort of next phase where models can use tools starts to look really practical. So imagine a system that can pull data from a spreadsheet, run a quick statistical test, and then summarize those results in plain language. Or an agent that can comb through 50 PDFs and extract only the methods section for comparison. For educators, agentic systems could manage grading rubrics, generate draft feedback, or even simulate different pedagogical strategies. The point isn't full automation. It's freeing up your time for higher level thinking. So we have LLMs and computer vision, and we have agents. But the world doesn't live in silos of data or modality-specific tasks only. We're not always looking for text-in, text-out processing. The world is images, sounds, videos, data streams, and physical signals. Multimodal AI combines our silos together and pulls different inputs and outputs. Multimodal models can describe an image in plain text. They can answer a question about a chart or a graph, or they can generate images from text prompts. And they can do this by bringing these different modalities into the same shared space of meaning. So the technical is this. Multimodal models turn everything, words, images, sounds, into an embedding in the same vector space. So text tokens already have embeddings, images are broken into patches and then embeddings, but audio can also be split into chunks and embedded. And once everything lives in this shared space, a model can compare text to images, can generate images from text, and it can turn sound into text. This shared embedding space is the foundation of multimodal AI. But in order for AI to take an input in one form, say an image, and produce an output in another, like text, that input first needs to be translated into the shared embedding space. I've mentioned the transformer architecture before, but let's open it up just a little bit, because the transformer isn't just one thing. It's a whole system of parts working together. So up front, we have encoders. Their job is to translate each modality into embeddings, the numerical language that the model can understand. And these encoders are tailored to the type of data. So text passes through a tokenizer and an embeddings layer, images go through a vision transformer encoder, and audio might use a spectrogram encoder to turn sound into patterns. And once these inputs are encoded, the transformer aligns them with a joint representation, that shared space where different types of information can actually recognize and relate to each other. A sentence, a picture, even a sound clip can all coexist and interact mathematically in the same conceptual space. From there, a decoder can take that understanding and translate it back out, reversing the process to generate a new output in the desired format. So whether that's producing a caption for an image, describing a sound, creating a picture from words. And this is the moment where it all connects, where text, images, sound, and action meet in that shared embedding space. And the machinery of encoders, transformers, and decoders, and tool calling finally lets AI see, speak, understand, and act as one system. So it's all coming together. So we're unified. Fantastic. What now? With this unified understanding, AI is no longer limited to digital tasks. So we are breaking the next frontier through systems that can take all of these capabilities and bring them into the real world through robotics. Physical AI means that machines can see and interpret their surroundings, plan and make decisions in real time, act safely and precisely in physical environments. AI powers robotics with 3 layers of capability. Perception. Sensors and cameras feed data into the AI models, often vision transformers or other multimodal models, so that the robot can recognize objects, people, and environments. Planning. The system decides what to do next, often using agent-like loops. Set a goal, predict possible actions, evaluate outcomes, and refine. And control. The lower-level motor control systems that translate those plans into movement. So a robotic arm turning 15 degrees, or a drone adjusting its altitude. In other words, perception tells the robot what's happening, planning decides what should happen next, and then control ensures that it actually happens safely. Physical AI could then, in many ways, be seen as the culmination of everything I've covered. So robots bring together computer vision to perceive their environment, language models to follow human instruction, multimodal models to integrate vision, text, and sensor data, and agents to plan multi-step tasks and adapt in real time. And when all of that is combined with physical hardware, you get systems that can interpret complex instructions, like go to Dr. Bumgardner and ask what time our meeting is, execute physical steps with precision, so the robot has a map of the office and it plans those movements to Dr. Bumgardner's office, goes in, asks him what time the meeting is. Dr. Baumgartner says, the meeting is at 8. The system can learn and adapt from feedback over time. So it's learned that everyone leaves the office around 6 p.m., so logically, it is unlikely that he means 8 p.m. Therefore, the meeting is at 8 a.m. So I've got an image on this slide of Temmie, which is our speaking robot that rolls around our office and smells things. So he's got a smell sensor on him that detects ammonia. And we hope to use this in a hospital setting where a robot might be able to detect if a patient has soiled themselves. But he also has a fall detection system and is capable of going and asking people in the office questions or giving strangers direction. So I know that was a lot to cover in a relatively short amount of time. So what can you do with all of this information? Well, start by thinking about your work. Do you have any problems or annoyances? Are there any blockades? Now that you understand what AI can do and how it does it, think about situations that inhibit your work. Do you have too much data that you couldn't possibly process manually? Are you afraid of missing big insights from your data? Maybe you're trying to summarize findings in hundreds of journal abstracts. AI can summarize and surface those patterns faster. Do you have a bunch of repetitive tasks keeping you from focusing on higher-level work? AI can format citations, extract tables, and automate regular processes. Do you feel stagnated or stuck in your ideation? Do you fear that there are ideas that you haven't thought of yet? AI can accelerate discovery by exploring connections, identifying gaps, and sparking ideas. So think about how AI could be a collaborator, helping you expand the reach of your own work. I want to end here with some final advice. So I said it earlier, AI is not here to replace your expertise, it's here to extend it. So now that you know what's under the hood, you can start thinking, where in my work could these capabilities make the biggest difference? So as you go back to your own research or your own teaching, I'd encourage you to look for the friction points, those tasks that slow you down or those questions you wish you had more time to explore. And those are often the places where AI can lend a hand. Not by replacing your judgment, by expanding what's possible within it. So start small. Try classifying your data automatically, summarizing articles, or visualize complex relationships. Even small experiments can open doors to new discoveries.